So by the time we finish this deep dive, global enterprise IT spending will have grown by, well, several $million.
It's wild to even think about.
Just sit with that for a second, right? The latest forecasts from Gartner for 2026 predict this absolutely staggering global IT spend of $6.15 trillion.
Trillion with a T.
Yeah, trillion. Yeah. And data center systems alone are surging by, I think it's 31.7%, just blowing right past the $650 billion mark.
Oh, yeah, it's a massive boom.
And behind all those commas and zeros is this insatiable corporate appetite for AI infrastructure. But underneath that shiny, future-focused spending boom is a very dark, a very expensive secret.
It really is the elephant in the server room right now.
Totally.
I mean, companies are authorizing these massive budgets to build out next-generation AI and cloud-native architectures, right? And they're operating under the assumption that moving to the cloud, specifically to containerized systems like Kubernetes, is going to significantly lower their total cost of ownership.
Right, the classic promise of the cloud.
Exactly. They expect to flip a switch and just watch their infrastructure bills plummet. But for a frightened number of organizations, I mean, the exact opposite is happening. They are modernizing, and they are just bleeding cash in the process.
Which is really the core focus of our deep dive today. If you are an IT executive, a CIO, or even a tech professional managing a sprawling infrastructure portfolio, this is your reality.
It's what keeps them up at night.
Exactly.
Yeah.
You did everything the industry playbook recommended. You modernized. You containerized. Yet your budget is, it's just ballooning out of control.
Yeah.
So today, we are taking the sources you've provided, the research, market data, operational analyses, to really figure out why cloud migrations are failing to deliver those promised savings.
And we really need to expose the deadly financial trap of, well, what we call parallel infrastructure.
Yes, parallel infrastructure.
Mm-hmm.
And we're going to explore the real-world friction of Kubernetes, and most importantly, lay out a hard-hitting executive playbook to finally turn off those expensive legacy systems.
Because to really grasp the magnitude of the problem, you have to look at the psychological reality of a massive migration.
Right.
We tend to think of these initiatives purely as like technical deployments, engineering teams get a mandate, move workload A from the old on-premise servers to the new Kubernetes cluster.
For just a standard IP project.
Right. But treating a migration merely as a technical deployment is the original sin. That's what leads directly to parallel infrastructure.
Okay, let's break down this idea of parallel infrastructure. I was trying to conceptualize what this actually looks like for a business.
It's not pretty.
No, it's not. Imagine you decide to build a state-of-the-art, highly automated smart home. You take out a massive mortgage.
Okay.
It's got solar panels, automated climate control, facial recognition locks. I mean, the works.
Sounds nice.
Right. But when move-in day comes, you look at the complex digital thermostat, you look at the smart locks, you think, oh, what if the Wi-Fi goes down? What if I get locked out?
The anxiety kicks in.
Exactly. So just to be safe, you decide to keep paying the rent on your old drafty apartment across town.
Oh, wow.
You sleep in the new house, but you keep all your old furniture in the apartment, and you keep paying the landlord every single month. Indefinitely.
I mean, that is a brutally accurate representation of enterprise IT in 2026.
Really?
Oh, absolutely. The new cloud-native architecture is up and running. The engineering teams did the grueling work of containerizing the legacy applications, meaning they, packaged the software and all its dependencies into an isolated unit that can run anywhere.
They did their job.
They did. They spun up the Kubernetes clusters. They built the CI/CD pipelines to automate software updates. They cut the ribbon, and management applauded.
The slide decks looked incredibly green.
Very green. Very successful board meeting.
But they never actually told the landlord they were moving out.
Exactly. They never flipped the switch to shut down the old estate. The legacy infrastructure stays fully operational.
So you're paying for both.
Right. The financial result is that the modernization bill becomes cumulative, not corrective. You didn't replace a $1 million cost center. You just stacked a new $2 million cost center right on top of it.
Man, the meter's running on both. And when we look at the software side of the Gartner data, they're projecting software spending to hit $1.43 trillion in 2026, growing at 13.3%.
It's a massive acceleration.
It is. And if you are running parallel infrastructure, you are effectively paying a massive portion of that software spend twice.
You are.
Walk me through the literal ground-level mechanics of where this money is evaporated. Like, what are the specific overlapping costs?
Well, the redundancy is staggering when you actually look at the line items. First, just consider legacy software licensing.
Okay.
You are still paying exorbitant annual licensing fees to legacy vendors for database software, operating systems, middleware, all the stuff you supposedly migrated away from.
Just paying for the privilege of having it sit there.
Exactly. You're paying for specialized hardware support contracts just to keep aging servers on life support. And then there is the storage crisis.
Right, the storage data from Gartner.
This is deeply concerning right now because, as the Gartner data highlighted, the industry is currently experiencing a memory shortage.
Which slows down smartphones and PCs.
Yeah, but it also heavily impacts enterprise storage arrays. Enterprise storage is becoming significantly more expensive, and parallel infrastructure means you are duplicating your entire storage footprint.
Oh man, so you're storing petabytes of the exact same data twice.
Twice. And you're paying a premium market rate for both because of the shortage.
So you have a CFO staring at a spreadsheet where the company is buying twice the amount of premium shortage-impacted storage just to hold duplicate data.
It's a nightmare for the finance team.
I bet. And beyond the silicon and the licensing, there has to be a human toll to this too, right?
Honestly, the human cost is arguably the most destructive part. You have operations teams, sysadmins, platform engineers, who are now tasked with managing two entirely distinct paradigms of computing.
They're doing two jobs.
Exactly. They have to retain all the tribal knowledge required to keep a 20-year-old monolithic application running while simultaneously trying to master the intense, distributed complexity of a Kubernetes environment.
The context switching alone must be exhausting.
It's brutal. It leads directly to burnout, high attrition, and an increased rate of critical errors in both environments.
Okay, let me challenge this narrative for a second.
Go for it.
If I am a CIO and my finance team is showing me these line items, the duplicated storage, the dual licenses, the massive cloud bills, and I know it's bleeding the company dry.
Right.
Why do my engineering teams keep doing it? I mean, these are brilliant people. They know the company is paying twice. Is it just a lack of skill? Or is there something inherent to Kubernetes that absolutely terrifies them into keeping the old systems running?
It is absolutely not a lack of skill. The driver here is an incredibly rational human emotion, which is fear.
Fear of what?
Specifically, the fear of causing a catastrophic production outage. Let's just look at the incentive structure for a site reliability engineer.
Okay, let's look at it.
No engineer gets a massive bonus for saving the company $10,000 in cloud compute costs.
Sure.
But they will absolutely get fired if they under-provision a new environment and take down the company's flagship e-commerce platform on Black Friday.
Oh, instantly fired.
Right. Therefore, the dominant engineering culture defaults to a practice called over-provisioning for safety.
They are buying their own psychological safety using the company's cloud budget.
That is the exact mechanism. To ensure the new cloud environment never crashes, they pad their resource requests in Kubernetes. They demand more CPU and more memory than the application has ever historically required.
Just in case.
Just in case. They implement incredibly conservative scaling limits. I mean, Kubernetes has robust auto-scaling features, right? Meaning it can automatically add or remove computing power based on real-time traffic.
Right, that's supposed to be the main benefit of the cloud.
It is, but teams often underutilize these features because they simply do not trust how the system will react under a sudden massive spike in load.
And the fascinating thing about Kubernetes is that it doesn't care. It is a completely agnostic engine.
Very agnostic.
Our sources describe it as honest infrastructure. What does that actually mean in the context of a billing cycle?
Well, it means Kubernetes does not negotiate, and it does not optimize for your wallet unless you force it to.
Okay.
If you tell Kubernetes, hey, I might need enough computing power to handle 10 times my normal traffic plus an extra 40% just because I'm anxious.
And what does Kubernetes do?
Kubernetes will say, no problem, reserve all of those resources and just hand you the bill.
Wow.
It bills you for the complexity and the capacity you ask for, regardless of whether a single customer ever actually hits that server.
So you end up with a severely bloated, deeply over-provisioned cloud cluster running right alongside a fully functioning, highly expensive legacy stack. Which leads us to a massive realization, right? The root of the financial bleed isn't the technology. The technology is doing precisely what it was engineered to do.
Perfectly.
The actual failure is in the measuring stick the executive team is using. The way leadership defines, tracks, and rewards a cloud migration is fundamentally broken.
Yeah, the corporate scoreboard is entirely misaligned with economic reality.
How so?
Well, if you ask almost any enterprise IT organization how their cloud transformation is going, they will proudly point to a single metric:
What do you think?
Percentage of workloads migrated. They'll say, we're doing great. We have migrated 85% of our applications to the cloud.
I mean, that sounds like a massive success on a quarterly earnings call.
It sounds like success, sure, but it tracks motion, not economic outcomes. It's a vanity metric.
The vanity metric.
Yeah. If you move 99% of your applications to a shiny new Kubernetes cluster, but that final remaining 1% of workloads requires your legacy mainframe, your old cooling systems, your legacy networking gear, and your old vendor contracts to remain active,
Then you haven't saved anything.
you have effectively saved $0. In fact, you've drastically increased your operational complexity. This is why the entire paradigm needs to shift.
Okay, so what's the new paradigm?
Cloud migrations cannot be treated as IT deployment projects. They must be treated as product retirements.
Product retirements. That shifts the entire psychology of the project. It goes from building the new thing to destroying the old thing.
It is a radical reframing. An IT project focuses on standing up new infrastructure. A product retirement focuses on the intentional, safe, and complete dismantling of a cost center.
That makes total sense.
Because a migration only generates return on investment when the old cost structures evaporate. If a migration plan lacks hard, unyielding exit criteria, a literal checklist for when the power gets cut to the old servers, the natural engineering default will always be to leave the lights on just in case.
So if we go back to the housing analogy, tracking the percentage of workloads migrated is like throwing a massive catered block party to celebrate that you have moved 95% of your furniture into the new smart home.
Right.
But you are still sleeping on an air mattress in the empty apartment because you haven't moved your bed yet. And you're still paying the landlord.
Yes.
The celebration is completely unearned. The only time you should pop the champagne is the moment you hand the keys back to the landlord, break the lease, and walk away forever.
That is the only moment that matters to the balance sheet. Consequently, the only metric that executives should be tracking is time to legacy switch off.
Time to legacy switch off.
Not how many apps are in the cloud, but how many days until we sever the legacy vendor contract. If that timeline is vague or undefined, the migration is fundamentally incomplete.
Let's extrapolate the danger of this a bit, bringing in the Gartner data on artificial intelligence.
Oh, this is critical.
They noted that spending on generative AI models and infrastructure is projected to grow by 80.8% in 2026. Every company is in a desperate arms race to integrate AI into their business processes.
Everyone wants AI.
Right. So what happens to an organization that attempts to deploy advanced generative AI while they are still dragging the anchor of parallel infrastructure?
It is a recipe for systemic failure. AI workloads, particularly generative AI, are extraordinarily resource intensive.
They need a ton of power.
They require immense compute power, rapid data retrieval, and highly optimized networking. If your organizational foundation is already suffocating under complexity debt, meaning your data is fragmented across legacy databases and new cloud silos,
And your teams are burned out.
right, your engineering cycles are entirely consumed by maintaining dual environments, you cannot build a viable AI strategy.
You just don't have the runway.
You'll be building these incredibly advanced, data-hungry models on top of untidy, bloated, and financially unstable foundations. You simply will not have the engineering bandwidth or the capital to do AI correctly because your resources are entirely tied up keeping yesterday's architecture on life support.
It's like trying to install a hyperdrive on a ship that is currently taking on water from two different holes.
Exactly.
So if time to legacy switch off is the absolute holy grail metric, we need to address the reality of the boardroom.
Let's do it.
How does a CIO actually execute a legacy shutdown without breaking the business?
It's incredibly easy to say turn it off on a deep dive, but doing it in a Fortune 500 company without causing a massive disruption is another game entirely.
It is.
Our sources outline a very specific executive playbook for decommissioning. Let's break down the pillars of this framework, starting with the very first prerequisite.
The first pillar is defining exit criteria. And this is the most frequently skipped step in cloud modernization. Really? Skip the most?
Oh, constantly. Before engineering is even allowed to touch a legacy system, there must be explicit, documented, and agreed upon retirement conditions.
Like what?
Like, what specific performance benchmarks must the new cloud application hit? What is the acceptable latency? What are the specific user acceptance criteria?
How many days of error-free operation do we need?
Exactly. How many days of stability in the cloud before we consider it a success? If you cannot clearly define what safe to shut down looks like before you start, You're not planning a migration.
You are planning to run parallel infrastructure.
Yes. Defining exit criteria is setting the destination coordinates.
Okay, so you have the destination, you know what it takes to turn it off.
Yeah.
But defining an exit is useless if you are flying blind financially while you build it.
Very true.
How do you actually see the financial bleed happening in real time, rather than just waiting for the quarterly budget review?
That requires implementing early cost and performance observability, which is a core tenet of FinOps.
FinOps, so financial operations.
Right. FinOps is a cultural practice that brings finance, IT, and business teams together to master the unit economics of the cloud.
So everyone's on the same page.
Ideally, yeah. Traditionally, engineering teams instrument their applications solely for technical health. They build beautiful dashboards showing CPU usage, memory utilization, and error rates.
But no money metrics.
None. They are completely blind to the financial telemetry.
Right. The developer sees that the application is running smoothly, but they have no idea that the specific database query they wrote is costing the company $400 an hour to execute.
Precisely the issue. Teams often ignore the financial realities until the very first massive invoice arrives from the cloud provider.
And by then it's too late.
By then, the architecture is baked in and the over-provisioning habits are deeply entrenched. To stop this, you need day zero visibility.
Day zero.
You need dashboards that show the technical metrics right next to the dollar signs. When an engineer requests a massive persistent storage volume just to be safe, they need to immediately see the monthly financial impact of that request right on their screen.
Make them feel the cost.
You have to expose the cost of anxiety so you can correct those bad habits early.
You can't optimize a system you can't see. But let's move from the engineering floor to the executive suite, because the sources emphasize making business owners accountable.
Yes, step 3.
And I want to push back on this heavily.
Okay, let's hear it.
In theory, this makes sense. But let's play out the reality. Let's say I am a business owner. I run a department that processes $10 million in transactions every single day.
Okay.
My legacy system, while old and clunky, processes those transactions reliably.
As legacy systems do.
Right. The IT team comes to me and says, hey, we built a new cloud version. We want to shut down the old one next week.
And you say,
I look at them and say, absolutely not. The cloud version had a microsecond of latency yesterday. My bonus is tied to revenue, not your IT budget. Leave the legacy system running.
and that is exactly what happens.
How does a CIO win that fight? How do you overcome the uptime at all costs argument from a stubborn business leader?
That is the exact friction point where most migrations stall indefinitely. The technical team lacks the corporate authority to force a business owner to accept operational risk.
They just don't have the leverage.
Right. The sources are brilliant on this point. They say, things rarely get turned off by committee. They mostly survive because of one.
Wow. Survive because of one.
Nobody wants their fingerprints on the decision that might take down a revenue stream.
So how do you force their hand?
You weaponize their own P&L against this legacy system.
Weaponize the P&L. I like that.
You do not argue with them about modernization or latency or cloud-native theory. They don't care about that.
No, they care about their numbers.
So you translate the abstract concept of technical debt into a literal hard invoice.
Okay, how does that conversation go?
You sit down with that business owner and you say, look, your department's application is currently running perfectly on the new cluster. Because you are refusing to sign the authorization to retire the old server, your specific department is now being charged an overlapping penalty of $45,000 every single month.
Ouch.
And that is coming out of your departmental budget effectively immediately until you authorize the sunset.
Oh, that changes the math instantly.
Yeah.
It takes the cost out of the ambiguous, centralized IT budget and drops it right onto their personal scorecard.
It creates an immediate behavioral shift. When a business owner sees that their hesitation is actively cannibalizing their own operating budget, their tolerance for minor cloud latency suddenly increases.
Funny how that works.
Miraculously, they find the motivation to accept a shutdown date. You align the financial incentive with the technical goal.
I appreciate that tactic. Money is the ultimate language in the boardroom.
Always has been.
But let's say the executives are aligned. The business owner agrees. We still have the engineers actually trying to execute this in the trenches.
Which brings us to step 4.
Right. If we just hand a massive, raw Kubernetes cluster to a team of application developers and say, good luck, don't overspend, we are setting them up for failure.
A spectacular failure.
The sources talk about investing in platform engineering as a shield. Why is this necessary?
Because a massive misconception in the industry is that giving developers raw access to Kubernetes is empowering them.
It's not.
It is not empowerment. It is an abdication of architectural responsibility. Kubernetes is incredibly complex.
Right.
Application developers want to write business logic. They want to build features for customers. They do not want to spend 3 days learning how to configure an ingress controller or how to write software-defined networking policies.
So what does platform engineering actually do?
Platform engineering involves creating a dedicated team whose sole purpose is to treat the internal developers as their customers.
Oh, internal customers.
Exactly. They build an internal developer platform, or IDP. This platform abstracts the terrifying complexity of raw Kubernetes away from the developers.
It hides the messy stuff.
It provides them with sane, pre-configured defaults. It provides standardized automated deployment paths. And most importantly, it institutes strict guardrails.
Guardrails like what?
Well, it prevents a junior developer from accidentally provisioning a massively expensive multi-region cluster when all they needed was a tiny sandbox environment to test a code change.
A very expensive mistake.
Very. The platform layer protects the developers from creating an economic incident, allowing them to move fast without breaking the bank.
The platform is the bumper lanes in the bowling alley. It keeps the ball out of the financial gutter.
Great analogy, yes.
But this brings us to a crucial pivot in our deep dive. Even with an internal developer platform, the underlying operational friction of Kubernetes is still there, right?
Oh, the complexity doesn't vanish. It just shifts.
Right. We have to look closely at the day-to-day management of these systems, specifically how visual management tools are becoming, well, mandatory to tame this environment.
To understand the necessity of visual tools, we must first understand the intense operational hurdles of Kubernetes.
Because it's famously difficult.
The complexity of Kubernetes is not a bug, it is a design feature. It was originally developed from Google's internal Borg system, so it was built to offer massive planetary scale flexibility and resilience.
But wielded by normal people.
Right. Wielding that kind of power requires a deeply intimidating foundation of knowledge.
What specifically makes it so difficult for a traditional IT operations team to adopt? I mean, they know computers.
They do, but traditionally an operations team might interact with infrastructure through visual interfaces or, relatively straightforward command line tools. Kubernetes demands an understanding of advanced Linux kernel namespaces, complex DNS resolution across dynamic IP addresses, and intricate software-defined networking rules.
It sounds like a lot.
It is, and the primary way you interact with all of this is either through a deeply unforgiving command line interface called kubectl, or by writing raw YAML files.
Let's talk about YAML because it is the source of so many late-night engineering nightmares.
It really is.
YAML stands for yet another markup language, though some argue it stands for YAML ain't markup language. It is how you declare what you want Kubernetes to do. But from what our sources indicate, it is incredibly fragile.
Fragile is a good word for it.
Explain the mechanics of why YAML causes so much friction.
YAML is notoriously verbose, and crucially, it is strictly reliant on indentation.
Wait, like spaces?
White space matters. Unlike programming languages that use brackets or semicolons to define structure, YAML uses spaces.
Literally just the spacebar.
Literally just spaces. If an engineer is defining a massive, multi-tiered application deployment and they accidentally use 3 spaces instead of 2 spaces on line 450,
What happens?
the entire file is invalid, the deployment fails, or worse, the deployment succeeds but with unintended catastrophic configurations.
A single tap of the spacebar can bring down an e-commerce platform. That is terrifying.
It happens more often than you'd think.
And then you combine the fragility of YAML with the highly abstract networking concepts in Kubernetes.
Exactly. Let's look at the mechanics of Kubernetes networking because it completely breaks the mental model of a traditional sysadmin.
Okay, how so?
In a traditional data center, a server has a static IP address. It sits in a rack, it has an IP, and you route traffic to it.
Simple enough.
In Kubernetes, applications run inside containers, which are grouped into things called pods.
Pods.
But pods are ephemeral. They are born, they do their job, and they die. They are constantly being destroyed and recreated based on load or node health.
So they don't stick around.
No. And every time a pod is recreated, it gets a completely different IP address.
Wait, so how on earth does any traffic actually find the application if the IP address is constantly changing?
That is where the concept of a service comes in. A service in Kubernetes acts as a stable, static IP address and a load balancer.
Okay, that makes sense. But how does the service know which constantly changing pods it is supposed to route traffic to?
It does not use IP addresses. It uses labels and selectors.
Break that down. How does a label work mechanically?
A label is simply a key-value pair, like app.frontend or tier backend.
Just a text tag.
Basically, when an engineer creates a pod via a YAML deployment, they attach these labels to it. When they create the service YAML, they define a selector that says, hey, route all incoming traffic to any pod that currently possesses the label app, front end.
Ah.
The service constantly queries the cluster's API, finds any pods with that exact label, and funnels traffic to them regardless of what their current IP address happens to be.
It is brilliant dynamic engineering, but I can instantly see the human vulnerability.
It's glaring.
If the connection relies entirely on matching text strings across different massive text files, the margin for error is huge.
The vulnerability is massive. If an engineer manually types the label app, front end in the service YAML, but makes a slight typo and writes app front end without the O in the deployment YAML,
Oh, no.
the service will search the entire cluster, find 0 matching pods, and drop all incoming traffic into a black hole.
And the application just goes offline.
The application goes offline completely. It is a massive source of misconfiguration, downtime, and operational panic.
And when a team experiences that kind of panic, what do?
They retreat to the safety of the legacy system they haven't shut down yet. The complexity directly fuels the parallel infrastructure trap.
Wow. This is exactly where the sources introduce visual management platforms like Container.
Yes.
How does graphically visualizing the cluster solve a fundamental networking typo?
Visual management tools completely alter the interaction paradigm. Instead of an operator staring at hundreds of lines of YAML text in a terminal, hoping they spot a missing space or a typo.
Straining their eyes at 3 a.m.
Right. A tool like Portainer allows teams to visually interact with the cluster. It abstracts the YAML generation behind a graphical interface.
So they aren't typing the labels manually.
No. If you need a service to connect to a deployment, you don't type matching labels into 2 different files. You graphically link the components in the user interface, and the platform mathematically ensures that the underlying YAML it generates is syntactically perfect and the labels match exactly.
You are mathematically reducing the surface area for manual human error. You are taking the fragile typing out of the equation.
You are. Furthermore, these visual tools aggregate the chaos. They provide comprehensive dashboards that summarize those critical telemetry metrics we discussed earlier.
The FinOps metrics.
Exactly.
Yeah.
CPU usage, memory consumption, disk I/O, all in a highly digestible visual format.
Which connects perfectly to solving the over-provisioning trap.
Yes, it ties right back.
If a FinOps analyst or an operations engineer can look at a visual graph and plainly see that an application requested 16 gigabytes of RAM,
But a flat green line shows it has never used more than 2 gigabytes over the past 90 days.
then they don't have to guess. They have the visual evidence to confidently right-size that allocation, cutting the waste without the fear of causing an outage.
The visual proof builds the operational trust required to finally pull the plug on the legacy alternative.
It also provides a critical bridge for teams migrating from simpler architectures. Many teams are accustomed to Docker Compose, which is a much simpler, more linear way of managing containers on a single machine.
Right. Docker Compose is much more approachable.
Moving straight from the relative simplicity of Docker Compose to the distributed complexity of Kubernetes YAML is a massive cognitive leap.
It's a wall.
So visual tools allow teams to manage both Docker environments and Kubernetes environments side by side within the same interface during the transition.
They can learn the relationships between Kubernetes objects visually rather than hitting a wall of command line complexity.
It de-risks the transition phase.
Absolutely.
But visual tools don't just solve YAML syntax and resource limits. The sources strongly indicate that they tackle one of the most dangerous hidden risks in a cloud migration. A risk that every CIO needs to understand immediately.
The security risks.
The nightmare of security and permissions.
We are moving into the territory of catastrophic vulnerabilities now. Let's examine the mechanics of Kubernetes role-based access control, commonly referred to as RBAC.
To set the stage for this, how does someone even log into a Kubernetes cluster? Does Kubernetes have its own username and password database?
Interestingly, no. Kubernetes, by design, does not inherently manage user identities or authentication.
So it doesn't know who anyone is.
It completely outsources that responsibility. It
Right.
relies on external identity providers. Typically, an enterprise will connect Kubernetes to their corporate Active Directory, or they will use a protocol called OIDC, which stands for OpenID Connect.
Okay, OIDC.
OIDC is an identity layer built on top of the OAuth 2.0 protocol. It allows the Kubernetes cluster to verify the identity of the user based on authentication performed by a secure external server, like Google Workspace, Okta, or Microsoft Entra.
Okay, so the external system, via OIDC, tells Kubernetes, yes, this person is John from accounting, let him in.
Correct. That handles authentication, proving who you are.
Right.
But once John from accounting is inside the cluster, what is he actually allowed to do? Can he view applications? Can he delete databases? Can he change networking rules?
That's the authorization part.
Exactly. That authorization is entirely governed by Kubernetes RBAC. And this is where the critical architectural flaw in human implementation occurs. Kubernetes RBAC is additive only.
Additive only. Explain the mechanics of that. It means you can only grant permissions, you cannot explicitly deny them.
That is the exact mechanism. In many traditional security systems, you might have a rule that says, John is in the developer group, so he has read access, but explicitly deny him access to the production finance database.
Makes sense.
Kubernetes does not work that way. In Kubernetes, roles stack and accumulate. If John is assigned a role that allows him to read all pods, and later he's assigned another role for a specific project that allows him to delete pods in a certain namespace, those permissions merge.
Oh, I see.
Because there is no explicit deny mechanism, resolving exactly what a user can and cannot do becomes incredibly mathematically complex as roles pile up.
So imagine a real-world scenario. An engineer moves from the quality assurance team to the production reliability team.
Okay, common scenario.
They get assigned the new production roles, but nobody remembers to manually strip away their old QA roles because the YAML is too complicated to parse.
Yep.
They just keep accumulating power.
The accumulation of power is the exact danger, because managing these sprawling additive YAML configurations becomes so unwieldy, and because developers are constantly screaming that they're getting access denied errors when trying to deploy critical patches.
The admins get frustrated.
Administrators experience friction fatigue. To just make things work and get the developers off their back, an administrator will intentionally bypass the granular roles and simply grant the user or the service account universal cluster admin rights.
Cluster admin. That sounds like the keys to the kingdom.
It is absolute, unrestricted, God mode access to the entire cluster.
Oh, wow.
It allows you to delete everything, view all secrets, alter any configuration. When teams are struggling with the CLI and raw YAML, cluster admin becomes the easiest way to solve permission problems.
Just give them everything so they stop complaining.
Right. But in a modern enterprise environment where you might have massive multi-cloud deployments spanning AWS, Azure, and Google Cloud, or hundreds of edge computing clusters operating at retail locations,
That's a huge attack surface.
handing out over-permissioned access creates sweeping existential security vulnerabilities. If a hacker compromises a single container that has been lazily granted cluster admin rights, they can pivot and systematically take down or encrypt the entire global infrastructure.
It is a ransomware operator's dream. It really is.
So how does centralized visual management stop the cluster admin creep?
Visual management pulls the RBAC configurations out of the abstract YAML and maps them into a clear, auditable graphical format.
So you can actually see what's happening.
An administrator can look at a dashboard and instantly see the exact matrix of who has access to what across every cluster globally from a single pane of glass.
No more digging through files.
It allows them to easily audit permissions, revoke excessive access, and ensure that the principle of least privilege, meaning a user only has the exact minimum permissions needed to do their job, is actively enforced.
Rather than abandoned simply because the command line was too difficult to parse.
Exactly. Visualizing security makes it manageable.
Okay, that covers the human access part. But the sources also dive heavily into a methodology called GitOps. This is a massive buzzword right now.
Oh, everyone is talking about GitOps.
How does GitOps fit into this operational picture, and what does it fundamentally change? GitOps is a paradigm shift in how we deploy and manage infrastructure. To understand it, you have to understand that Kubernetes is an inherently declarative system.
Declarative meaning?
You do not give Kubernetes a list of imperative commands like create server A, then install software B. Instead, you declare the final desired state. You say, I want 3 instances of software B running.
And Kubernetes just figures it out.
Kubernetes figures out how to make that happen. GitOps takes that declarative nature to its logical conclusion. It mandates that every single configuration, every deployment rule, and every infrastructure setting must live as code in a version-controlled Git repository like GitHub or GitLab.
So Git, the same system developers use to track changes in their application code, becomes the absolute single source of truth for the entire infrastructure.
Exactly. If a configuration is not committed to the Git repository, it legally does not exist in the infrastructure.
Wow.
But the true magic of GitOps is the mechanical engine that drives it, the reconciliation loop.
Break down the reconciliation loop. How does it work mathematically under the hood?
Imagine a software agent running continuously inside your Kubernetes cluster. Its entire existence is a constant, endless loop. Every few seconds, this agent looks at the external Git repository, which is the desired state.
Okay.
Then it looks at the actual current state of the live cluster. It mathematically compares the two.
Checking for differences.
Exactly. If an engineer manually logged into the cluster and changed the settings, say, they increased the number of pods from 3 to 5 to handle a traffic spike, but they didn't commit that change to Git.
The system catches it.
The reconciliation engine detects the drift. It says, the Git repository says there should only be 3 pods. The cluster has 5. The cluster is wrong.
And what does it do? Does it alert someone?
It doesn't just alert. It takes autonomous immediate action.
Wait, really?
It ruthlessly deletes the 2 extra pods, forcing the live cluster back into perfect synchronization with the Git repository. It continuously corrects drift without human intervention.
That is incredibly powerful for consistency. But I can see how that autonomous behavior would be terrifying for a team that isn't used to it.
It can be a shock.
If something goes wrong and an engineer is trying to troubleshoot a silent, invisible loop via the command line while it continuously overwrites their manual fixes, it would induce panic.
It causes immense frustration for teams new to the methodology. And this is where visual interfaces become critical for GitOps adoption.
Bringing it back to visibility.
Right. Integrating the GitOps reconciliation engine into a visual dashboard allows teams to instantly see the synchronization status. They don't have to query the command line to figure out why their changes are being reverted.
They can just see it.
They can look at the screen and see a glaring visual indicator that says the cluster has drifted from the Git repository. They can see exactly which specific lines of configuration are conflicting.
That's huge.
It demystifies the autonomous loop, making this incredibly powerful methodology accessible and safe for a much wider range of operational skill levels.
Let's pull this all together for the executive listening right now. If I am a CIO, a CFO, or a VP of infrastructure, I am ultimately focused on the balance sheet.
Of course.
I frankly do not care about the mathematical elegance of a reconciliation loop, the syntax indentation of YAML, or the OIDC authentication flows.
No executive does.
Right. Why should I care that my engineering team is investing in internal developer platforms and visual management tools?
You should care deeply because those granular, highly technical weeds are the exact friction points that dictate your financial risk profile and your migration timeline.
So it all comes back to time and money.
Always. If your highly paid engineering team is spending 80% of their week manually debugging thousands of lines of YAML syntax, struggling to untangle additive RBAC permissions, and fighting silent GitOps reconciliation loops, your migration timeline is going to stretch for months into years.
The project just stalls.
The operational friction will grind the project to an absolute halt.
And while they're stalled, the meter on the parallel infrastructure keeps running.
Exactly. Visual tools and platform engineering accelerate operationalization. They allow your teams to master the complexity, move faster, and deploy safer.
And by moving faster, you drastically shrink the window of parallel infrastructure.
Yes. You accelerate the timeline to reach that singular vital metric, the legacy switch-off date.
Getting to the finish line.
Investing in tools that simplify technical complexity is a direct, causal pathway to saving the company millions of dollars in overlapping infrastructure costs and finally realizing the promised ROI of your cloud transformation.
Time is money. And in the world of cloud migrations, time spent confused by complexity is literally duplicated infrastructure money.
It really is.
We have covered a massive amount of ground today. We have diagnosed the economic disease of parallel infrastructure.
We have.
We have fundamentally shifted the framework from celebrating workloads migrated to executing rigorous product retirements. And we have established that equipping your teams with robust platform engineering and visual management tools is the only way to overcome the operational complexity that causes these devastating financial delays.
Now it is time to move from theory to immediate, measurable action.
Absolutely. Knowledge without execution is just trivia. The value is in the application. We need to focus on what happens when you take off your headphones.
What's the next step?
Based on the hard truths in our sources, we are issuing the 48-hour executive challenge.
A 48-hour challenge. I like it.
If you are an IT leader listening to this deep dive, do not schedule another vague strategic cloud alignment workshop. Do not sit through another slide deck celebrating the percentage of workloads you've moved to Kubernetes.
Please don't.
Instead, within the next 48 hours, I want you to isolate one major legacy system in your organization that is currently languishing in the partially migrated phase.
Every organization has at least one of these zombie systems. Find the most expensive one.
Find it. Then pull in your FinOps lead or your finance team and calculate the literal hard monthly cost of running both the legacy version and the new cloud version simultaneously.
Do the real math.
Calculate the overlapping software licenses. Calculate the duplicated vendor support contracts. Calculate the premium costs of the duplicated storage arrays.
Get a highly specific dollar amount.
Put that single number on a slide, walk into the responsible business owner's office, and hand it to them. Use the sheer weight of that financial reality to force a realistic, mathematically sound, and non-negotiable sunset date for the old system.
It is the single most effective tactic for cutting through institutional inertia. When the abstract cost of indecision is quantified into a literal monthly penalty, executive priorities align and decisions get made rapidly.
Let's do a final recap of the reality we are operating in. We are navigating a $6.15 trillion global IT landscape.
It's massive.
The massive capital investments required to integrate generative AI and build the future leave absolutely zero room in the budget for the wasteful maintenance of yesterday's architecture.
None.
Success is no longer defined by simply stating, we are running on Kubernetes. True, measurable cloud success is defined exclusively by the statement, we successfully turned the old thing off.
We turned it off.
Implementing disciplined exit criteria, leveraging FinOps observability, and deploying visual management tools to tame the technical chaos are the essential keys to safely executing that switch off.
The required shift in perspective is profound. It is no longer sufficient to just be a builder of the new. Leadership must become highly disciplined demolishers of the old.
And as we wrap up this deep dive, I want to leave you with one final lingering question to ponder as you look across your own infrastructure portfolio.
What's the thought?
We have spent the last hour dissecting the financial cost of operational fear. The fear of turning off legacy systems because they might disrupt the business. The fear that directly fuels over-provisioning, bloated clusters, and parallel infrastructure.
Right.
But consider this provocative angle. What if the legacy systems your organization is most terrified to shut down, the ones you treat with the most reverence, are actually the systems providing the absolute least real competitive value to your customers today?
Oh, that's an interesting thought.
What if the immense accumulated technical complexity of those old monoliths is simply functioning as camouflage, disguising the fact that they are functionally obsolete?
That is a critical evaluation. We are highly prone to confusing a system's fragility and maintenance cost with its actual business importance.
Are you paying a premium to protect a system that the market outgrew a decade ago? It is a question worth asking before you pay another month of overlapping bills. Thank you for joining us on this deep dive into the realities of cloud economics. Take a hard, objective look at your parallel infrastructure, find that zombie system, quantify the bleed, and go start turning things off. We will see you next time.